Okay, the equilibrium constants that we're going to talk about are Q and K, and they give information or measure the equilibrium of reactions. So Q is called a reaction quotient, K is the equilibrium constant. Both Q and K have commonalities, but there is a clear differentiation. So let's start with reaction quotient Q. So it measures the status of a reversible reaction, which just means that we can go from reactants to products and then products back to reactants, right? We do this back and forth, which is true for most reactions, right? There are some cases of irreversible reactions, but most of the reactions that we'll talk about are reversible. We derive Q from the stoichiometry of the balanced equation only, and we write the reaction quotient only for gaseous and aqueous species. We ignore liquids and solids. So liquids and solids are not included in our equilibrium constant expression, Q. Okay, so let's look at the reaction where we have reactants A and B forming products C and D. M, N, X, and Y are our stoichiometric coefficients for the reactants and products. So reaction quotient would be the concentration of the products C and D raised to their coefficients over the concentration of each of our reactants raised to their coefficients. So this is the expression that we write for our reaction quotient Q. And we write Q sub C because this is written in terms of concentration, right? We can also write it in terms of partial pressure, but in this case, it's Q sub C because we're talking about concentration. So if we look in this expression, if we proceed in the forward direction, the reactant concentrations will decrease, right? Because reactants are being consumed. So our denominator will also decrease, right? To reflect the reactants being consumed. And as a result, our expression or our reaction quotient, Q sub C, will increase. So if we think about proceeding in the reverse direction, we'd expect the opposite. Okay, so pause this video and write the concentration-based reaction quotient for the following reaction. This is me freezing while you pause the video. Okay, welcome back. So notice that our reactants and product are all in the gaseous phase. So all of them will be included in our reaction quotient. And this is what our expression is. So we have product SO3, right? Its concentration raised to a power of 2 because that is our coefficient, over the concentration of SO2 raised to its coefficient 2, and the concentration of O2 raised to a power of 1, its coefficient. So this is the concentration-based reaction, I don't know why I'm making this word up, reaction quotient. All right, so before I go to equilibrium constant K, I just want to stress this again. So in this example, we wrote it based on concentration, but we can also write this based on partial pressures as well. We can also write it based on partial pressures as well. All right, so our equilibrium constant K, right, as the name of it hints, it is a constant at equilibrium. So it turns out that it's equal to our reaction quotient at equilibrium. So it's only dependent on temperature, right? It doesn't change with time, concentration, or pressure. And It can also be expressed using concentration as well as partial pressure. And we denote the difference with our subscripts here, right? C for concentration, P for partial pressure. So let's look at the same example, right? The same reaction. What would be our equilibrium constant expression? Well, just like our reaction quotient, it would be K sub C equals the product concentrations raised to their coefficients over the reactant concentrations raised to their coefficients. So it's written, the expression is basically the same for our equilibrium constant as our reaction quotient. And that's what I mean by it has commonalities. Let's look at another example. So in this case, we're going to write K sub P, the partial pressure for this reaction. And it's the same idea, but we just write it with a P. So P is for pressure, and we put what product or reactant as a superscript. As a subscript. So we have P for pressure. This is the pressure of our product, CH3OH, or methanol, over the partial pressure of hydrogen gas raised to its coefficient times the partial pressure of carbon monoxide raised to its coefficient, which is 1. So K sub C, K sub P, whether we are writing it based on concentration or pressure, it's written the same. We just write it differently, right? As P for pressure versus the brackets for concentration. All right, so same stoichiometric derivation as with concentration when we are also writing the equilibrium constant in terms of partial pressure. Now, their expressions are the same, Q and K, right? But what is the difference? There is a clear differentiation. So Q, our reaction quotient, is calculated at any moment. So as the reaction proceeds, right, it doesn't immediately jump to equilibrium, but we can write Q at any moment. Q can be calculated at any moment. And it also is used to determine if the system is at equilibrium or which way it will shift. And we're going to come back to that in another video. Now with our equilibrium constant K, it's a constant at a given temperature, but it represents the ratio only at equilibrium. So basically Q it gives us information about where the reaction is in reaching equilibrium, and we can write it at any moment, whereas K is only written at equilibrium. So that's the difference between our equilibrium constant Q and K. So this law that talks about this differentiation is the law of mass action, which basically says at a given temperature, the reaction quotient for a system or a reaction at equilibrium is constant, and it is equal to our equilibrium constant,